Already slides out there as a comment already.
We should give it away. We should have a picture of you giving it away.
It's a John, he would freak. He would freak the fuck out. He's like, you know, you can talk to people, but don't give away all the information. Yes?
Ismael, please.
My name is Ismael, and nice to see you here. I come from the CTVR Research Center. I'm going to present this libLTE. It's a modular open source library for LTE. There's other people involved in this project, Paul Saturn from the CTVR too, and Book, who is with Virginia Tech, and Tony, who is from UPC in Barcelona. libLTE is a very new project. We just started this January. It's a library for LTE. With a library, we mean that it's not an application. We don't want to make a eNodeB, a base station, or a user terminal. We just want to provide a collection of modules that then you can use to implement your base station. But of course, we will provide a reference implementation of a base station and a mobile terminal. It's a modular library. With modular, what we mean is that we want to be able to, if you are only interested in one of the modules of the library, to be able to pick it and use it in your application. For those of you who usually use libraries, you have found probably that sometimes it's very difficult. Maybe you're interested in only a piece of the library, and it's very difficult to get it and use it in your own software. Also, we want it to be computationally efficient. That means that we don't want to just implement the standard in a naive way. We want to be clever. For instance, if you have to make a convolution, you can use the FFT convolution, these kind of things. Also, one of the objectives is to avoid dependencies with other libraries or frameworks, to facilitate the portability to embedded systems, for instance. But it's true, and we have seen it today, is that GNURadio, for instance, has a huge number of users, and if you want your application to be used by other people, you have to provide some way for these GNURadio users to use it. And also we have other SDR frameworks. We have seen Iris here, but we also have ALOE. I will talk a little bit after, and SCA, which is a military framework for software radio. So we want somehow to enable these framework users to use this library. In this table, I summarize the related projects on LTE. The first one is the Marisoft software. It's probably the best software on LTE that we have today, but unfortunately, it's proprietary. It is able to run in a quad-core in real time with 2 antennas, 20 MHz bandwidth, and they implemented the eNodeB as well as the MME, but also it works on the N210 user, but unfortunately it's proprietary. We also have the OpenLTE. As far as I know, it's also quite complete. It implements the PHY and MAC layer and partially the RSC layer, but unfortunately it's not modular. If you are only interested in some of the DSP blocks, it's very difficult to isolate it because there are many dependencies between modules. We also have the GNURadio, but also as far as I know, it only implements the synchronization and decoding of broadcast signals. PBCH is the physical broadcast channel in LTE, and also it uses Boost library. We also have this LTE cell scanner, which doesn't use a framework, but also only implements the synchronization and the decoding of the broadcast channels. And it uses IT++. IT++ is a very good library, but when you move to an embedded system, it's very difficult that it can run it. And finally, there's also OSLD, which is a project I was involved in. This was also an LTE downlink application for this ALOE framework, but this framework was very focused on distributed real-time processing, and so it wasn't easy to use for the people. So yes, why do we want another LTE library? The first thing is that we want to, as I said, to enable the reuse of modules. We want to enable portability. C++ or Boost are difficult to find in some embedded platforms. And we would like to avoid the necessity to use a framework. If you want to use it, you can use it, but sometimes it's too much overhead, and also it's very hard to move one module from one framework to another. And finally, efficiency. It's, as I said, it's not only implementing the standard. So we have this objective, modularity. We want to be able to generate code for frameworks, and we want efficiency. And the design that we approach is a two-layered interface for the modules. At the low-level API, we don't impose any rule to the designer. The designer can implement the DSP block as he wants. And then we define a high-level API where we do specify some rules. Finally, the idea is not using all the well-known libraries like FFTW or bulk, but if they are available in the system, use them. This is an example of how the low-level API is defined. As you see, there is any rule. I mean, the programmer defines his initialization and function, and to deallocate the memory, and then you can set options, you can get options. Typical interface without any restriction. But then you have this high-level interface where we do specify these three functions, for instance, that you typically see in all the frameworks. All the frameworks start with an initialize function, and then they have a work function, which is called periodically to perform the DSP, and then a stop function. The idea is that the DSP designer has to implement these functions calling the low-level API functions. Also, we define this structure which needs to be followed, where you can see that the designer specifies the parameters that must be that configure the module at the beginning, and then some runtime input or output parameters that this module accepts or produces. From this, all this is defined in a .h file, and from this, using the Python's C library, we parse this header, and using a Python script, we convert this module specification to a general XML file. Then from this XML file, you can implement, using another script, you can generate automatically the C or C++ files that your framework needs. For instance, now we only have this Python script that generates the module for this framework for ALOE, but it shouldn't be difficult for someone to implement this Python script to convert the XML file to a GNURadio module. So the idea is that with the same library of modules, we can generate code for very different frameworks. How do we work? Typically, I mean, here I try to describe how we are working with this library. You start with a MATLAB model, and we use a reference base station, which happens to be the Marisoft, because it's much cheaper than a signal generator, professional signal generator. And then we implement our receiver code of a specific functionality. Then we move to a live base station, a live signal that we capture from the base station, and we check that our receiver code is working properly. And finally, we make the transmitter, we check against the receiver that we know that is working with the standard, and we verify that the signal generated by the transmitter is the same than the others. This diagram shows a little about the modular structure of the library. At the bottom you have small modules, each implementing a DSP block. For instance, the Viterbi, the scrambling, the range matching, or the CRC. These modules have minimal intermodule dependencies. So if you are only interested on the precoding of the LTE, you can take this file and move it to your application. On the other hand, as you move up to in the layers, obviously you start finding more dependencies. For instance, the synchronization algorithm uses this set of files. This is for decoding the primary synchronization signal to estimate the channel. So if you are interested on the synchronization, then obviously you find some dependencies. Well, this is the directory structure of the library. We organize the blocks in categories, and there is a single .h file that the programs using this library need to include. And okay, what we've done so far, we implemented a real-time cell search program. Scans an LTE band and looks for base station and synchronizes with them. Later, if we are lucky, we will try to find some LTE base stations. I don't know if we will find some. The LTE synchronization is aided uses two signals which are sent by the base station, the primary and the secondary synchronization signal, which are transmitted every 5 milliseconds. So the receiver needs to perform a correlation with 3 possible PSS sequences every 5 milliseconds. This is very complex, so you need to try to be clever on how to implement this. Otherwise, you will consume all the resources only for synchronization. You also have to do carrier frequency offset estimation, and in most of the cases, sampling frequency of the offset estimation. The CFO, you can estimate it from the cyclic prefix or from the PSS. What we do is to use the PSS because it's more accurate. And to estimate the sampling frequency offset, what you do is you observe the variation in the times that the PSS has been set. Finally, well, this is what the cell search program does. It scans an entire band. First, we look at the received signal strength, and for those bands where we observe that the signal power is high enough, we try to correlate the PSS. And if you find the PSS, then we track the signal for n frames, and we estimate the CFO and SFO and the cell ID. Well, to implement LTE is a very complex waveform, and if you want to be able to run it in real time in a laptop, it's very hard. To start with, the sampling frequency is a problem because not all hardware has the 3.84 clock. For instance, the N210 doesn't have it, so you need to resample. Resampling is very expensive, but as Tom pointed out before, the FFTW has a very good performance, even if the length of the DFT is not a power of 2. So maybe one of the solutions is not sampling at the clock that you should sample, but then not changing the length of the DFT. Another problem is the synchronization. The synchronization is transmitted is sampled at almost 2 megahertz, 1.92, but the signal only uses 1 megahertz, so you could sample at 1 megahertz. Well, exactly 945. Also, using a time domain correlation is very expensive. You should use a DFT-based correlation, and then once you find the peak, narrow your search only to where this signal is supposed to be. Decoding is also very expensive, especially a turbo encoder, and it needs a very high throughput. So this is something that should be done probably to use SIMD instructions. Bulk, for instance, exactly. But implementing a turbo encoder with bulk probably is not easy.
Yeah, you can do it.
And also multi-user detection is also a problem at the base station, especially synchronization and detection. This little bit the roadmap of this project. We started with the downlink. In most of the physical channels of this downlink, we already have some code from this OSLD project that I was involved in before, and this code can be reused. For the uplink, also, most of the parts are the same as the downlink and can be reused, but there are still many things to do, like the SIMD decoder, the MIMO, and integrating all the pieces. To summarize, libLTE is a library, and we aim at modularity. We want to be able to use this library, only parts of this library or all the library in embedded platforms with no framework dependencies or third-party libraries. And I take the opportunity to call for contributions, either in MATLAB models or C implementations are welcome. If any of you is working on LTE or something related, any kind of implementation is welcome. And that's it. Thank you very much. If there is any question. Any question?
How do you correct the sampling frequency offset?
Yeah, actually now we don't correct it because for the synchronization, the correlation is robust against the sampling frequency offset. We are able to detect it, and we will show in the demonstration later that we are able to detect it. But correcting is very complex, especially if the offset is very small. But yes, this is a problem.
But are you planning to do this or just resynchronize every frame?
Yeah, exactly. If the offset is small enough, you can resynchronize every framework. You just you lose some SNR. That's all. Any other question?
You estimate carrier frequency offset and the sample frequency offset, but shouldn't these two normally be linked by the internal oscillator or the receiver?
Yeah.
Can you repeat the question for the audio?
Yeah, I think he asked if we estimate the CFO and if it's related to the offset of your oscillator. Was it the question? Yes.
Because they are linked by the reference oscillator in the receiver itself. It would
Yeah.
be cool if a future hardware platform, maybe it already does it, uses a VCTCXO instead of a normal oscillator, so that you could control the frequency a little bit and then you could solve both of these problems at the same time. You could just tune the reference clock of your receiver to move the sample rate.
Yeah, but not But first of all, you cannot do that with all the receivers.
Yeah.
And the second thing is that in LTE, correcting the carrier frequency offset is very easy. Estimating it is very easy, very simple computationally speaking, but correcting it is also very easy. The sampling frequency offset is a little harder, but as we said, if it's small enough, it's only synchronizing every 5 milliseconds and you solve the problem.
You explain a bit how you do if it's so easy to estimate?
Yeah, to estimate the CFO, correcting it is very easy. You multiply by a phase. Yeah. And to estimate, you have two ways. You can use the cyclic prefix, and what you do is you look at the angle of the output of your correlation. Yeah, because you are transmitting the same sequence, so you look at the phase shift. And if you have already synchronized with the primary signal, this PSS sequence, which is transmitted by the base station, you know how this sequence looks like. There are only 3 possible sequences. And once you have correlated and you are synchronized in the time domain, at the output of the correlator, you also look at the phase shift between that you have at the output of your correlator. And this gives you the CFO.
Yeah, but well, for the first, you measure the speed, the rotation speed of the receiver?
Yeah.
It's the same setup around the Baker Schmidl and Cox. It's a standard carrier frequency offset estimation algorithm.
It's in the standard?
Yeah, well, it is a standard approach. It's used by kind of most synchronization techniques for OPM. So like Schmidl and Cox and the part I was talking about earlier, if you look at that paper, it's there.
And the SFO?
So the SFO.
No, for the SFO, you look at the variation on your. I mean, when you synchronize, you know what the time offset. So if you look at the time offset every frame, you get an estimation of the SFO.
If it's very small?
If it's very small, you need more time.
And then you go out of sync.
No, if it's small, you don't go down.
Exactly. If it's small enough, you only synchronize at every 5 milliseconds.
Because
you don't need
but you don't need to estimate
it's too small,
it.
you don't need to estimate.
Yeah.
But if you want it, so
Yeah. If you want it, you could do it, but then you don't have to resynchronize and just estimate in, let's say, 100 frames, which is the offset.
incorrect. Yeah.
But if it's that small, correcting it will be very
It's
complex.
a fractional reason.
Exactly. And it's a huge fraction of the sample.
Depends on the implementation.
Yeah.
Then you probably don't need it because your noise will spread it so far that it doesn't matter anymore.
Yeah.
And you still have the phase noise of those later small drifts you have. You will not see it.
There is no tracking impact. That's what you are talking about. You estimate for one frame the frequency offset, and you think it's constant for the frame.
No. I mean, you can do it, but your estimation is not very good because it's subject to variation.
But if you use just the prefix, how do you do that?
No, we were talking about sampling frequency
Yeah.
offset, not carrier frequency.
Amir was talking about.
Yeah. There were two different questions.
Because
No, but for the carrier frequency offset, that's also true. You have to average over 100 or 50 frames. Each frame is 5 milliseconds, and well, the more accurate you want your CFO estimation, the higher the delay on synchronizing with the network.
Because there is no feedback, it's only open.
Yeah,
Open.
there's no feedback.
Okay, I would like move the other questions to the open session at the end. I'd like to thank Ismael again.